In this example, the figure shows a U-shaped conducting rail. So here's our conducting rail that's oriented vertically in a horizontal magnetic field. So what we have here is something that's upright like this, and the magnetic field is like this. Okay, so it's up, and then the magnetic field is perpendicular to that. The rail has no electric resistance, so no resistance here, no resistance here. Oh wait, sorry, no, this does have a resistance. No resistance here in the rail, but this is a bar, a slide wire. It has a mass M and resistance R. That one's allowed to move up and down with no friction in these points, but it is still in contact with the rail, so we still get a conducting loop. We release this slide wire from rest. The first thing it asks us to do is show that the slide wire reaches a terminal speed and find an expression for that terminal speed. So terminal speed's probably something you're familiar with. A terminal speed is a constant speed. For example, when skydivers jump out of a plane, they fairly quickly reach a terminal speed due to the drag force of the air. The drag force of the air is proportional to the velocity, so it just increases and increases till they come to a constant speed. Same sort of deal happens here, except it's not air resistance, it's a magnetic resistance. Okay, so let's get started. So we let this go from rest. There's a force due to gravity on it, because remember this loop is upright. So when we let the slider go, gravity pulls on it and it will start to fall down. Since there's a force of gravity on it, it begins to fall down. So slide falls, and it falls because of gravity. As the slide falls, what we get is an increasing magnetic field, and in this picture that's into the page. So there's an increasing magnetic field. This is a conducting loop, so what's going to happen is that there's going to be an induced field to oppose that magnetic field. What's the direction of the induced field? Well, if we're making more field into the page, then what we're going to get is induced field out of the page. Let's draw that induced field. Because it wants to counteract the fact that there's now more field into the page. So this is going to be our B induced. So this leads to induced B out of the page. What's the result of that induced magnetic field? If I imagine I'm grabbing onto this bottom wire here, I know that magnetic fields make circles. Right here the magnetic field is coming out of the page and shows my thumb pointing towards the right. So I get an induced current in this bottom part that points towards the right. And then because it's a closed loop, the current can come up here, and down here. That's the induced current. So if there's an induced field out of the page, there's an induced current, which in this picture is counterclockwise. Counterclockwise. If there's an induced current counterclockwise, what's the induced force going to be? So we'll use our right-hand rule. Current goes to the right, thinking about the bottom part here now, what's happening on that slider. Current is to the right, field is in, force is up. And that's an anticipative result, because we know that the induced magnetic force will oppose the motion. It will slow it down. So there's our induced magnetic force. So the induced magnetic force opposes the motion. So before we get going, let's figure out what is that induced magnetic force, and then we'll see how we're going to figure out what the terminal velocity is. So we know that the induced force is equals IL. They use a lowercase l here in the picture, so I'll use a lowercase l too. IL cross B. The magnitude will be I times L times B, J hat, because it points up. So now some things to figure out is what are I. So I, we remember Ohm's law, then current is potential. It's going to be our induced potential divided by resistance. So before we can finish our expression for current, we need our expression for induced potential. We get that from Faraday's law. The magnitude of our induced potential, because we already know the sign, the direction of the current and stuff, so we don't have to worry about the sign on the potential. The magnitude of the induced potential is d phi dt, change in magnetic flux over time. Magnetic flux is magnetic field dotted with the area, B dot A. B and area are in the same direction. The area of the loop is the length times the width of the loop. I'll call this guy W for width. We can take our constants out front. B is a constant, L is a constant. We're left with B times L times dW dt. This is change in distance over change in time. That's equal to the speed of the loop. So let's put this potential in our expression for current. Let's put this current in our expression for force. Now we can just make it look a tiny bit nicer. The induced magnetic force is B squared L squared divided by R times V J hat. So our induced magnetic force, the takeaway is that the induced magnetic force is proportional to the velocity. What that means is that the force will increase as the speed gets bigger. So the force is going to increase as the speed gets bigger. It's going to increase up to some maximum value. So you might ask, why does it have to have a maximum value? Why can't it just increase, increase, increase? Well, just like a drag force in air, this magnetic force opposes the motion. So as it gets, this magnetic force can never exceed the downward force, because if it got bigger than the downward force, it would start to pull upwards. It would be going with the motion, and that's not how an induced magnetic force works. Induced magnetic force always opposes the motion. So you would see as it started to rise, your magnetic force would go in the opposite direction. So your magnetic force will increase until this thing starts to go at a constant velocity. So it's going to increase until it hits a maximum value of Fg. So when that happens, Fb plus Fg equals 0, which tells us that the acceleration equals 0, which tells us that the speed equals constant, and that constant value is the terminal velocity, which we call V with a T subscript. Okay, so let's work that in. So the expression for our magnetic force is B squared L squared V over R. That's going to have the same magnitude as the weight, m times g. So they're equal when we're at terminal velocity. That tells us that terminal velocity is m times g times r divided by b squared L squared. So there's our expression for our terminal velocity. Next it says find your terminal velocity if the length of the wire is 20 centimeters, the mass is 10 grams, the resistance is 10 ohms, and the magnetic field is a half a Tesla. So we'll put in our mass of 10 grams times g, 9.81 meters per second squared, times the resistance, which is 10 ohms, divided by our magnetic field, 0.5 Teslas squared, divided by the length squared. The length is 20 centimeters or 0.2 meters. and we get a terminal velocity of 0.981 meters per second, about 1 meter per second. So that's how fast that's going to slide.